So, good afternoon, Doc. Good afternoon, classmates. I am Carisha Faber Naldez, together with my partner, Ma'am Nika Mata. We'll be presenting the topic on physical development, the brain, body, motor skills, and sexual development. Okay. Before anything else, let us first define physical development. So, physical development refers to the development of body structure and its components. It includes the height, weight, skeleton, muscles, bones, teeth, and body proportions. So, in other words, it is the development of outer physique and external factors of a particular person. So next is height and weight. So weight is one of the best criteria for assessment of growth and a good indicator of health and nutritional status of a child. So the average birth weight of a child is 2.8 to 3 kilograms. So initially, a baby loses weight, but it regains it by 10 days after their birth. The weight doubles by 4 to 6 months of age. So later on, the weight gain is very less. That means the rapid is less. The weight triples by the end of their first year, and the weight gain is low during the second year of age because they spend more energy, di ba? If kabantay mo mga bata, hilig maglakaw-lakaw, magkuan, sitting, or mag-iyak, no? So because of that, um the weight gain is low. So again, the weight increases rapidly during puberty, followed by weight increase to adult size. So when it comes to height, the average height of a newborn infant is about 50 centimeters, and the height measures around 60 centimeters when they reach 6 months of age. By the end of the second year, the infant gains height by 25 centimeters. Thereafter, there is an increase of 7.5 centimeters per year until the child reaches 7 years of age. So, the increase in height indicates skeletal growth. Yearly increments in height gradually diminish from birth to maturity. So again, BMI or body mass index. So BMI is important criteria which helps to assess normal growth. For example, is malnutrition or obesity. So the BMI of a person is computed by BMI equals to weight in kilograms divided by height in meters squared. So if the result of the computed BMI is more than 30 kilograms, it indicates obesity. And if it is less than 15 kilograms, it indicates malnutrition. So for the categories, if less than 18.5, it is underweight. The normal weight is 18.5 to 24.9. Overweight is 25 to 29.9, and obesity is a BMI of 30 and greater. So the head circumference is related to brain growth and development of intracranial volume. So the average head circumference is measured about 30 centimeters at birth. At 3 months, it is about 40 centimeters. At 6 months, 43 centimeters. At 1 year, 45 centimeters. At 2 years, 48 centimeters. At 7 years, 50 centimeters. And by 12 years of age, it is about 52 centimeters, which is almost the same as an adult. Fontanelle closure. So at birth, anterior and posterior fontanelle are present. So posterior fontanelle closes early by 6 to 8 weeks of age. Namo ni siya dire. And the anterior fontanelle normally closes by 12 to 18 months of age. So early closure of fontanelle indicates craniostenosis, which is a disorder in which there is early fusion of the sutures of the skull in childhood. It produces an abnormally shaped head and at times appearance of the face. Next is chest circumference. So chest circumference is an important parameter of assessment of growth and nutrition status. At birth, it is 2 to 3 centimeters less than head circumference. By 6 to 12 months of age, both become equal. After the first year of age, chest circumference is greater than head circumference by 2.5 centimeters, and by the age of 5, it is about 5 centimeter larger than head circumference. So, chest circumference is measured by placing the tape measure around the chest at level by placing the tape measure around the chest at the level of the nipple, so in between the child's inhalation and exhalation. So mid upper arm circumference or MUAC. So this measurement helps to assess the nutritional status of younger children. There is growth due to inadequate nutrition, which can be simple, particle, and useful measurement. Okay, so this is an example of MUAC. So the average MUAC at birth is 11 to 12 centimeters. So at 1 year of age, so by 1 year, 1 years old, it is 12 to 16 centimeters. By 12 years, it is 17 to 18. And by 15 years, it is 20 to 21 centimeters. Okay, next is eruption of teeth. So the time of eruption of the first tooth of the child varies and it depends on their heredity, nutrition, and health. So, girls are slightly advanced in teeth development than boys. So, the sequence of eruption is more important than the time of eruption as it may lead to the development irregularities. So, the first teeth appearance of the child are the lower incisors, no, for the child age 6 to 8 months, followed by the upper incisors. So molars appear later on. So when the child reaches 1 year, the baby already has 4 to 6 teeth, and by the second year, they have 16 teeth. Skeletal development. So what does it include? So the skeleton includes bone development. The earliest form of bone is cartilage, which is very soft and has pliable structure. The cartilage gradually becomes a bone through the process of ossification. No? The process involves deposition of calcium and other minerals on the surface of cartilage to make it hard and rigid. So, as most bones are not ossified during infancy, they are softer, more pliable, more sensitive to the pressure and sudden movements. And the rate of ossification differs from various bones. Some of the bones include the head and breast and ossify very early in life, while others mature later. So the soft spots in the skull ossify completely by 2 years old. There is a variation in boys and girls in bone growth. So girls are developmentally more advanced than the boys. Skeletal maturation or bone growth is an indicator of physiological development and continue up to 25 years of age. Okay, muscle development. So the neonate, or when you say neonate, this refers to a newborn child. So a neonate has all the muscle fibers. These fibers are small in relation to the overall size of the infants. However, during infancy period, muscles grow in size. They increase in length, breadth, and thickness. So the muscle development follows cephalocaudal, cephalocaudal direction and proximodistal direction. So that is the head and neck muscles develop early and the muscles of the trunk, arm, and legs. So changes in body proportion. So small children differ from adults in size as well as in body proportions. So after birth, the trunk and the limbs of the body grow faster, while the head growth slows down, giving rise to the smaller heads and longer limbs as the child grows older. An infant is rather chubby with a big head and small lungs. By the time the child reaches 6 years of age, his body proportions are equal and appear like those of an adult. The ratio of muscles and fat tissue contribute to the physique which characterizes each individual. Physique is usually established well by childhood and is continued into adulthood. So boys have more muscle tissues and the girls have more body fat. So changes of physical growth and development. So the boys and girls undergo a rapid physical growth in terms of height and weight, which is known as growth spurt. The growth spurt begins with weight gain of 26 pounds in boys and 20 pounds in girls. This weight gain is extremely due to accumulation of fat around the legs, arms, abdomen, and buttocks. The increase in height during the growth spurt is striking among the boys. So usually they grow 3 to 5 inches or 7 to 12 centimeters, and girls from 2.5 to 4.5 inches, which is equivalent to 6 to 8 centimeters. The age at which the maximum growth occurs approximately 14 years for boys and 12 years for the girls. and the difference remains to be consistent. So these are the physical changes that are caused by hormonal secretion, which can be seen during this adolescent period. Okay, so the brain grows at a surprisingly rate early in life, increasing from 25% of its eventual adult weight at birth to 75% of adult weight by the age of 2. So the last 3 prenatal months and the first 2 years after birth have been termed the period of the brain growth spurt because more than half of one's adult brain weight is gained at this time. So between the 7th prenatal month and a child's first birthday, the brain increases in weight by about 1.7 grams a day. However, an increase in brain weight is a general index that tells us very little about how or when various parts of the brain mature and affect other aspects of development. So let's take a closer look at the internal organization and development of the brain. So the human brain and nervous system consist of more than a trillion highly specialized cells that work together to transmit electrical and chemical signals across many trillions of synapses or connective spaces between the cells. So neurons are the basic unit of the brain and nervous system. So the cells that receives and transmit neural impulses. So neurons are produced in a neural tube of the developing embryo. So from there, they migrate along pathways laid down by a network of guiding cells to form the major parts of the brain. So the vast majority of the neurons a person will ever have. So some have 100 to 200 billion of them have already formed at the end of the second trimester of pregnancy. So before the brain growth spurt has even begun, until recently, it was thought that no new neurons were produced after a baby was born. However, scientists have established that the formation of new neurons in the hippocampus, which is an area of the brain important to learning and memory, occurs throughout life. So, what accounts for the brain growth spurt? One major contributor is the development of a second type of nerve cell called glia, which nourishes the neurons and eventually encases them in insulating sheets of a waxy substance called myelin. So glia are far more numerous than neurons are, and they continue to form throughout life. So influenced by the sites to which they migrate, neurons assume specialized functions as cells of the visual or auditory areas of the brain. For example, if a neuron that would normally migrate to the visual area of the brain is instead transplanted to the area that controls hearing, it will change to become an auditory neuron instead of a visual neuron. So individual neurons have the potential to serve any neural function, and the function each serves depends where it ends up. Meanwhile, the process synaptogenesis, the formation of synaptic connections among neurons, proceeds rapidly during brain growth spurts. So this brings us to an intriguing fact about the developing nervous system. The average infant has far more neurons and neural connections than adults do. The reason is that the reason is that neurons that successfully interconnect with other neurons um, crowd out those that don't, so that about half the neurons produced early in life also die early. Meanwhile, surviving neurons from hundreds of synapses, many of which will disappear if the neuron is not properly stimulated. If we imagine the developing brain to a house under construction, we might imagine a builder who merrily constructs many more rooms and hallways than he or she needs, and later goes back um, and knocks about half of them out. Okay? So, what is happening here reflects the remarkable plasticity of the young infant's brain. The fact that its cells are highly responsive to the effects of experience. The brain has evolved so that it produces an excess of neurons and synapses in preparation for receiving any and all kinds of sensory and motor stimulation that a human being could conceivably experience. Now, of course, no human being has this broad a range of experiences. So much of one's neural circuitry remains unused. Then, neurons and synapses that are most often stimulated continue to function. Other surviving neurons that are stimulated less often lose their synapses, which is a process called synaptic pruning, and stand in reserve to compensate for brain injuries or to support new skills. So note the implication that the development of the brain early in life is not due entirely to the unfolding of a maturational program, but is instead the result of both a biological program and early experience. Next is neural plasticity, the role of experience. So, how do we know that early experience plays such a dramatic role in the development of the brain and central nervous system? The first clue came from research by Austin Reason and his colleagues. So, Reason's subjects were recent subjects were infant chimpanzees that were reared in the dark for periods ranging up to 16 months. So his results were striking. So dark-haired chimps experience atrophy of the retina and the neurons that make up the optic nerve. So this atrophy was reversible if the animal's visual deprivation did not exceed 7 months, but it was irreversible and often led to total blindness if the deprivation lasted longer than a year. So neurons that are not properly stimulated will degenerate. No? Might we even foster the neural development of an immature, malleable brain by exposing participants to enriched environments that provide a wide variety of stimulation? So animals raised with lots of companions and many toys to play with have brains that are heavier and display more extensive networks of neural connections than those of literate mates raised under standard laboratory conditions. What's more, the brains of animals raised in stimulating environments lose some of their complexity. So if the animals are moved to less stimulating quarters. So in one human study, head circumference, A rough indicator of brain size was assessed in 221 children at a gestational age of 18 weeks, again at birth, and finally at 9 years of age. So the head circumference of children from high socioeconomic status homes and those whose mothers had earned college degrees were significantly larger than the head circumferences of children for low social economic status homes and whose mothers had no degrees. So even though genes may provide rough guidelines as to how the brain should be configured, early experience largely determines the brain's specific architecture. So the brain differentiation and growth. So not all parts of the brain develop at the same rate. So at birth, the most highly developed areas are the lower brain centers, which control states of consciousness, inborn reflexes, and vital biological functions such as digestion, respiration, and elimination. So surrounding these structures are the lower brain um, the structures are the cerebrum and cerebral cortex. So the areas most directly implicated in voluntarily bodily movements, perceptions, and higher intellectual activities such as learning, thinking, and language. So the first areas of the cerebrum to mature are the primary motor areas, no, which controls simple motor activities such as waving of the arms, and the primary sensory areas which controls sensory processes such as vision, hearing, smelling, and tasting. Thus, one reason human neonates are reflexive, sensory motor beings is that only the sensory motor areas of the cortex are functioning well at birth. So by 6 months of age, the primary motor areas of the cerebral cortex have developed to the point that they now direct most of the infant's movements. As brain cells proliferate and grow, some of the glia begin to produce a waxy substance called myelin, which forms a sheath around individual neurons. So this myelin sheath acts as an insulator to speed up the transmission of neural impulses, allowing the brain to communicate more efficiently with different parts of the body. Myelination follows a definite chronological sequence that is consistent with the maturation of the rest of the nervous system. So, at birth or shortly thereafter, the pathways between the sense organs and the brain are reasonably well myelinated. As a result, the neonate sensory equipment is in good working order. As neural pathways begin between the brain and the skeletal muscles myelinate, the child becomes capable of increasingly complex motor activities such as lifting its head and chest, reaching with its arms and hands, no, rolling over, sitting, tindog, and eventually walking and running. Although myelinization proceeds very rapidly over the first few weeks or the first few years of life, some areas of the brain are not completely myelinated until the mid to late teens or the early adulthood. For example, the reticular formation and the frontal cortex, parts of the brain that allow us to concentrate on a subject for lengthy periods, are not fully myelinated at puberty. So this may be the one reason that the attention spans of infants, toddlers, and school-age children are much shorter than those of adolescents and adults. So in addition, as myelinization enhances the efficiency between the more primitive emotive subcortical areas of the brain and the more regulatory prefrontal cortical areas of the brain, an infant or child's ability to process and respond to social important emotional input such as the expressions of fear or kanang disappointment, disapproval of an parent's face may improve. No? So the highest brain center, the cerebrum, consists of two halves or two hemispheres connected by a band of fibers called the corpus callosum. Each of the hemispheres is covered by a cerebral cortex, an outer layer of gray matter that controls sensory and motor processes, perception, and intellectual functioning. So, although identical in appearance, the left and right cerebral hemispheres serve different functions and control different areas of the body. So, the left cerebral hemisphere controls the right side of the body. So, as you can see in the image, it contains centers for speech, hearing, verbal, memory, decision making, language processing, and expression of positive emotions. The right cerebral hemisphere, on the other hand, controls the left side of the body and contains centers for processing visual spatial information. Non-linguistic sounds such as music, tactile sensations, and expressing negative emotion. Thus, the brain is a lateralized organ. So, cerebral lateralization also involves a preference for using one hand or one side of the body more than the other. So, about 90% of adults rely on the right hands to write, eat, perform, and other more motor functions, whereas these same activities are under the control of the right hemisphere among most people who are left-handed. However, the fact that the brain is a lateralized organ does not mean that each hemisphere is totally independent of the other. So, the corpus callosum, which connects the hemispheres, plays an important role in integrating the respective functions. So, through the ages, adults have noticed that when children reach the teenage years, they suddenly begin to ask hypothetical what if questions and to ponder weighty abstractions such as truth and justice. Are these changes in thinking tied to late developments in the brain? So many researchers now believe that they are. For example, myelinization of the higher brain centers, which continues well in adolescents, not only may increase adolescents' attention spans, but also explain why they process information much faster than grade school children. Furthermore, we now know that the brain retains at least some of its plasticity well beyond puberty, and that reorganizations of the neural circuitry of the prefrontal cortex, which is involved in such higher level cognitive activities such as strategic planning, continues until at least age 20. In addition, brain volume increases through early to mid adolescence and then decreases during late adolescence, suggesting that some pubertal reorganizations may involve synaptic pruning. So, even though changes in the brain during adolescence are less dramatic than those um, earlier in life, it is likely that some of the cognitive advances that teenagers display become possibly only after the brain undergoes a process of reorganization and specialization.